Now, if you'd followed my advice, you would have written down Bernoulli's equation right from the start to reassure yourself a little bit. And if we pick location 1 there and location 2, that would be Z1 plus P1 over rho g plus V1 squared over 2g equal to Z2 plus P2 over rho g plus V2 squared over 2g. That would be if there were no losses and no energy additions. So we had at 1 plus whatever we added in the pump minus whatever we lost due to friction along the way is what we'll have at the end. So there's our head loss due to friction, and we've also got a bunch of fittings and things that will lead to some minor losses. So writing the whole thing out in full, in detail, every time will help you avoid making mistakes. Make sure that you're only neglecting things that you really meant to neglect. Now that's atmospheric. That's equal to 0 because V1 is equal to 0. Nothing's really moving up here. But over here, the pressure is higher, it's 6 bars. V2 is actually a significant velocity, potentially. And we do have some height changes between Z1 and Z2. So when we simplify that to get the head rise across the pump, we'll have P2 over rho g. Right from there, we'll have Z2 minus Z1. And in fact, Z2 is lower than Z1. It's below the surface of the water. And we'll have V squared over 2g plus delta HF. So let's expand that out now. F L over D, V squared over 2g. Now that's V2 squared, and that one could be V2 as well. We're interested in the velocity in the pipe, and it's the same size pipe all the time, so it's all V2. Plus delta HM will be the sum of the K factors times V2 squared over 2g. So we can simplify this down. We know something about P2 over rho g. We know that Z2 minus Z1 is, what is it? There's Z1, and we go down 10 meters and back up 8 meters. So Z2 is 2 meters below Z1. So we'll wind up with the pressure term, our 6 bar, minus 2 meters of elevation. And that winds up being 59.3. So 59.3 is the useful work that the pump's got to do to overcome this 6 bars of pressure. And that about makes sense, because we know that each bar of pressure is about 10 meters ahead. And it's a little lower because of this -2 that shows up in here. Plus 1 plus FL over D plus sigma K times V squared over 2G. And we know all of these things now, so we can plug in the numbers and get something out. It's interesting to look at how those numbers all come together from a practical design standpoint. We've got our 59.3, which is the useful work we're doing. We've got to increase the head in the system in order to pump uphill to that higher pressure. We're going to lose due to friction along the way. 1 plus FL over D. F is 0.026, L is 45 meters, D is 0.0493 meters. Plugging through the numbers, that turns out to be 23.7. And Sigma K is 7.75. All times V squared over 2G. Or 59.3 plus, and here's where the numbers start to get a little more interesting, 42.7, whoops, let me check that number, 1 plus 23.7 plus 7.75 gives me 32.45 times V squared, 5.24 squared, divided by 2, divided by 9.81, gives me 45.4. Or a total of 104.7. Or I'm going to say just 105. I really don't think my answer is accurate enough to go to decimal places in that head rise across the pump. So delta H across the pump must be 105 meters. And more than half of that is useful work. The rest is losses. So that's probably not a terribly incorrectly sized system. If we made the piping a little bit bigger, we could go to considerably lower losses. On the other hand, there may not be enough energy being expended here to justify that increase. So, the question asked, what head rise across the pump is required to deliver a flow of 0.01 cubic meters per second from the reservoir to the receiver vessel with the conditions as shown? And this is the head rise that's required. And we can then use that information. We know that the pump should have a head greater than 105 meters for a flow equal to 0.01 meters cubed per second. So this gives us the head and flow requirements, and we can now go and source our pump. We can go looking for pumps that will actually do that particular task and compare them one to each other.